Hello everyone, it's a lovely sunny spring morning here. A warm welcome to you all, and I hope you're ready for an overview of connecting heat pumps to the electricity network. As you can see, we're in an MS Teams meeting. Your video and microphone have been disabled. That's by design. This is a presenter-led webinar. It'd be lovely to have a two-way conversation, but the numbers here would just make that impractical. You can, of course, interact via the chat facility, and we'll explain how that's done shortly. My name is Richard Park. I'm an electrical engineer and I work for Three Consulting. I'm currently at home here in Cheshire, England, and I'm joined by a small group of presenters and guests who are all getting ready backstage. You can see them on screen. For anyone that hasn't heard of Threepwood, we are an independent electrical power consultancy. We're based in the north of England, and many of our consultants have previously worked for electricity distribution companies. We are heavily involved in development of electricity documentation, things like standard specs, but also we work in electrical safety, procedures, audits. We do some work in electrical asset management and future networks, feasibility studies, network planning, new technology management. We would like to thank you for joining this webinar and taking the time out of your day. We want to pass on our knowledge of the subject so that the whole engineering community is better informed when making important engineering decisions. Today's presentation will cover a number of aspects relating to heat pumps, and we have a selection of speakers from Threepwood to cover these today. Asad Ali is a senior consultant, and he will cover technical considerations for heat pumps. Chelika Siame is a graduate, and she will talk a little bit about voltage flicker and one specific example of flicker. Paul Fiddler is a principal consultant, and he is going to talk about projections, heat pump projections, and Rio ED2. We also have some guest speakers, Beanland from the Heat Pump Federation and Dan Clark from the Energy Networks Association. Bean, do you want to give a little introduction to yourself and the Heat Pump Federation?
Sure. First of all, thank you very much indeed for having us. It's a pleasure to contribute to this webinar on what is a really important aspect of heat pump market development in the UK. For those that don't know us, the Heat Pump Federation was formed nearly 2 years ago. Our opening event was scheduled for the 19th of March 2020. You can imagine what happened to that. So we spent our first 2 years basically in lockdown, which has been very frustrating. But we've had some significant successes in building policy positions. The Federation is primarily a lobbying organisation, and we've had some really interesting success with both government bodies, agencies like Ofgem, and now we can get out and about. We're looking forward to achieving rather more over the coming years as heat pumps begin to start to move into the mainstream.
Excellent, thank you, Bean. Dan, would you like to give an introduction to ENA and yourself?
Hi Richard, yes, thank you. Hi everyone, great to be here today. Really important webinar on heat pumps. For those of you that haven't met the ENA or myself before, my name's Dan Clark. I'm the Head of Innovation here at ENA, and we are the trade association for all of the gas and electricity networks across the UK and Ireland. And as you can see from the slide, that's a lot of customers, a lot of miles of pipes and a lot of miles of wires as well. And essentially, we are the place where networks can come together and collaborate on some of the challenges facing the industry. Obviously, networks at the centre of our journey towards net zero. And so we see ourselves as a place where we can come together, collaborate both across electricity networks, gas networks, but also cross-vector as well, so whole systems approaches, and collaborating with other third parties such as yourselves and other trade associations like the HPA, consultancies like Threepwood. So really, really great to be here. We support networks in a lot of different areas, particularly how they can overcome some of the challenges of integrating low carbon technologies, and that's really what we're talking about today, particularly the impact of heat pumps and why it's really, really important for installers to notify networks when they are installing a heat pump, and perhaps the ways in which we can collaborate better with manufacturers to support installers in the process of notifications to networks. So without further ado, I'll pass over. I will be here for the whole of the conference or the webinar, and I'll be around for questions at the end as well. But I'll pass back to Richard. Thank you.
No, thank you, Dan. I mean, a really key point there, as you say, notifications, and that's something we're gonna probably keep banging on about. But before we get started, some housekeeping for you attendees. We will consider questions at the end. Please post these to the webinar, to the chat, I should say, to the chat. There's a chat function here. Assad's just going to add a little, I think there's been a few hellos and how are you doing type thing. So please add your questions there. Depending on how many we get, we should have time at the end. Obviously, if we don't have time, we will come back to them via email because this webinar is recorded, and we will circulate that recording along with the slides to all of the attendees. We can pick up on questions you may have missed out on, and there's a survey as well. So that'd be nice to hear your feedback on what you thought of it and whether you would like to hear more in future. So without further ado, let's get straight into the thick of it, and I'd like to welcome Assad to the table and talk about technical considerations. Assad, first question is really what's the most important thing about connecting a heat pump? What are the kind of the headline considerations?
Yeah, thanks, Richard. Morning, everyone. So the first thing obviously we've got to consider is the service rating. So that's because obviously we're adding heat pumps to the current network, and that's going to draw more current from the network. So we've obviously got to be a bit wary of what the cutout or the fuse can handle. I mean, older properties, I think they were 60 amp fuses, and the new ones are 100 amp. So first of all, we've got to make sure that the cutout / fuse is capable of handling the additional load. But also on top of that, we've got to look at the service cable that supplies the property. We don't want to obviously cause that to burn out. So we've got to make sure that the service cable is sufficiently sized for installing a heat pump. The other factor we've obviously got to look at is power quality. What I mean by power quality is harmonics. Again, harmonics will cause equipment to heat a lot more because the sine wave is not a full sine wave. So we've got to be careful of harmonics. That's inherently present in power electronic components, which heat pumps have. But also flicker, because flickers, once you're switching in a large, 3, 6, 9 kilowatt load, that's going to have an impact on the network.
Yeah. So I guess the question next is why are these things? Is there some mandate that we can point to, some high level sort of obligations of why these are important?
Yeah. So there's three main standards or legal obligations that DNO will have to comply with. The first one being ESQCR, which is a statutory obligation, and it specifies the requirements to quality of supply and safety. So quality, as I just said, power quality that we're referring to. So we've got to make sure that the equipment that's being installed does not affect the overall power quality of the network. And safety as well, like I said, fuse cutout ratings, service cables, for example. We want to make sure everything's correctly rated to allow for heat pumps to be connected. But also there's a D code, which is the distribution code. That's a license condition for network operators to operate. their networks. So all DNOs, network operators, have to abide by the distribution code, and that sets out the principles relating to the design of equipment according to the statutory obligations. So I just mentioned ESQCR, but also national specifications, for example, 61,000 series, which I'll go into, and ENA engineering documents.
You mentioned there's a third obligation or statutory requirement. What is that, asset?
Yeah, that's then the final one, the Emc Directive. So that is another legal requirement which applies to any equipment containing power electronics or electronic components, and that the purpose of the Emc Directive is to limit the electromagnetic emissions from the equipment. Obviously, when you install heat pumps and whatever else with low carbon technology, you want to make sure that it doesn't disturb already connected equipment, so radio, telecommunications. So the Emc Directive aims to sort of limit the amount of emissions that comes out such equipment.
So let's go back to that decode document. What are, and you said there's some technical standards. What can you give us a bit more information about what those technical standards are called up by the decode?
Yeah, so there's three main documents in the decode which are referenced. These are all ENA documents. So for the first one is P28, which is the voltage fluctuation document. So this document has 3 stages. So where a product complies with the product standards, you can then connect the equipment to the network, and then you have a stage 2. So if it doesn't comply with stage 1 and it complies with stage 2 limits, you're allowed to then connect, and then a final stage is stage 3, where a detailed assessment is required, which the DNO then has to carry out. So that's P28 for voltage fluctuations. Similarly, we've got G5, which is for harmonics. So again, you have 3 stages within G5. So obviously, depending on the harmonic emissions, the equipment can either be connect and notify. So you connect the heat pump, you notify the DNO that's been connected, or the DNO then needs to do some assessments, do some studies to make sure that the heat pump will not cause any disturbance to the network. And finally, P29.
Oh, excellent. I guess it's P28 and G5, which are most applicable in the case of heat pumps. So you mentioned the stage 1 there of P28 and P20 and G5, and there's some product standards. Can you tell us a bit more about those product standards and why they're important?
Yeah, so the product standards apply to all disturbing equipment, furnaces or air conditioners, or all sort of electronic equipment. So the main standards that apply to these sort of equipments are 3-2 and 3-3, so the 61,000 series for harmonics and flicker. For heat pumps, less than 16 amps. And then you have the technical requirements of 3-2 or 3-12 for equipment between 16 amps and 32 amps. Or you have 3-12 for anything above 32 amps for harmonics, and similarly 3-11 for flicker. One thing to note here is that although manufacturers test their heat pumps according to their standards, I think the point here which needs to be made is we need sufficient data. When I say we, I think DNOs need sufficient data to assess the heat pump, because they've obviously got to model the heat pump on their network and to ensure that the heat pump is able to connect to that particular point in the network. Yes,
yeah, good point. So I think that gives us a good overview of those product standards. I mean, there's the flicker and the harmonics. Chelika, you had you have an example, or you can tell us a bit more about flicker and maybe go through quickly an example. Are you okay to talk about that?
Yes, I am. Thank you, Richard. Hello, everyone. So our electrical network also has an impedance associated with this. This will change based on how close you are to the substation, whether you're in a rural or sort of an urban area. This is why when you connect a piece of equipment, this can be a cooker, an electrical shower, or even a refrigerator, there is a fluctuation or voltage drop due to the modulation in current. Now, this results in a phenomenon called flicker. This is not only irritating to the eyes, but it can also cause migraines, seizures, headaches, or damage to electrical equipment.
I guess what you mentioned there, the impedance and why that's important when I guess you're determining what flicker is. Can you tell us a bit more about how impedance is managed when you're assessing for flicker?
So the reason why you don't get DNOs being called all the time from customers complaining that their lights are flickering is because they are able to keep a lid on this using one of the standards, which is one that my colleague mentioned, 61003-3. Devices are being tested to a specific impedance, ZREF, which was obtained by an averaging technique for multiple utilities. Devices are tested to this device, and if you pass the limit specified in 61003-3, you can connect to the supply. However, if devices fail, they are subjected to conditional connection.
So ZREF is like the kind of the benchmark for unconditional connection. What are the parameters then that are measured when you're evaluating flicker, Celica?
So the first two, which is the short and long-term flicker, these refer to flicker severity. The short-term flicker should not be greater than 1, whereas the long-term flicker should not be greater than 0.65. The other two parameters, which are referred to as the D parameters, first of all, you have your maximum steady state voltage change, which should not exceed 3.3%. Then you have the time accumulated, where you have a maximum steady state voltage change greater than 3.3%. This should not be greater than 500 milliseconds. The last one, which is the absolute maximum voltage change or rapid voltage change, this has different values. It can either be 6, 4, or 7% based on the equipment that you're operating, but we're going to keep it to 6% for this because this is a device that we can manually turn on and off.
Yeah. Okay. So 6% is kind of probably what most heat pumps would have to comply with, but 3.3 is also important in the steady state. How do we measure this? How can we assess it, or how can we measure these quantities, Celica?
So there's 3 different ways in which you can measure it. The first one is using a flicker meter, but this is subjected to specific test conditions, and it gets much harder for larger devices. The second one, which is a computer-based simulation, you need to obtain the time-based varying voltage for your device. It is also subjected to specific test conditions. The third one that you get is a desk-based simulation, which is it allows for a much easier method of calculating. And the good thing about this is that the value that you obtain is at least within 10% of what you'd obtain if you just do a direct measurement using the flicker meter.
Yeah, I guess that depends on having accurate sort of characteristic there. You mentioned you've got there the starting profile. So if you did have the information to hand, what are the formulas that you would use as part of this desktop?
So I'm going to go through this slightly quickly, but the first equation that you need is what you need to obtain is the flicker impression time, which is the first one, and this is based on your shape factor, which is F. Now, the shape factor can be obtained from 61003-3. This is based on whether you have a ramp voltage change, a triangular or square voltage change. Then based on this value, you can then plug it into the other 2 equations to obtain your short and long-term flicker based on your observation period, which is TP.
Seems complex, Celica, but I guess once you've run the numbers, it starts to become clear where the result might be. Can you go through quickly an example that you've done?
Yes, so this is an example that we did on a much smaller heat pump, but it can also work on larger devices. So we did this on a 15-amp heat pump, which had a soft starter that limited its starting current by 50%. So we based it on our starting current profile. We made some assumptions on the running and the starting power factor, and we're able to obtain your rapid voltage change. And as you can see from this graph, it was able to meet all of the requirements.
Yeah. It's below 6% for the start, and the steady state is within the 3.3, so it meets everything. And is that you, Chelik? Anything else you want to say on that?
Yes. Oh, thank you. Yes. No, this just goes to show you that it does meet all of the requirements, including your short and long-term flicker.
Thanks, Chelik. Hopefully, people caught some of that. There's quite a bit there to think about. Assad, just coming back to you again, we've talked about these impedance values, and impedance is important, I guess, for both harmonics and flicker when connecting. Can you give us some sort of context to these impedance values?
Yeah, so I think as Chelika mentioned, impedance is important. I mean, that's what DNOs use when they do their calculations. It's all about impedance. So as an example, if we take a 32 amp device connected to a single phase supply, that then gives you impedance requirement of 0.218 ohms with a short circuit power level of 243 kVA. So you can see on the diagram, you've got your mains cable, and you've also got your LV service cable, and you've got your fuse which goes into your house. So that's 0.218 ohms for the at the PCC, which is just at the bottom there. Yeah, that's correct. But then you also have the requirement for flicker, which for a single phase device is 0.4 plus J0.25, which equates to 0.47 ohms on the point of supply, which is in your homes. So we've got to make sure that the cable is big enough to handle that impedance.
So just to clarify that, the first point here was harmonics, and you took an example of a 32 amp and tested to 312. The RSCE is assumed as 33, that's the default. So you've used that value and the 32 amps to determine an impedance of 0.218 at this mains cable position.
Yes, that's correct.
And then this is the ZREF, which is the default unconditional value in 3.3, is it?
It's 3-3, yes.
And that applies up here at the meter position. Okay.
Yes, that's correct.
So what? Yeah, you said these obviously are determined largely by cable lengths. Can you tell us some examples what cable lengths we're dealing with for these sort of stock defaults? Yeah,
so for example, if you have a 500 kVA ground mounted transformer at distribution level, which is sort of typical, an impedance at the PCC, which is just off the mains cable, is 0.218, and that equates to a length of 650 meters for a 300 wavecon cable. So which seems not too bad. I mean, it depends on where the substation is, but the one that we have to look at is the underground service cable. So for a 35 square mil copper concentric cable, a length of 200 meters would give you that impedance of 0.47. Yeah. So obviously you've got to be a bit careful when it comes to houses in villages and sort of rural areas, because obviously the substation is not as close, and that's I think where most of the problems probably lie. So you've got to make sure the cable's big enough to supply a heat pump in that area.
Yeah, I guess this here example shows it's very easy to sort of imagine all houses complying with this, but again, if a lower impedance is needed, these lengths are low, these lengths are less.
Yes.
And hence the conditional connection comes into play. Excellent. Thanks for that technical overview, Assad and Chelika. I was going to get Bean to run through some thoughts on from a heat pump manufacturer perspective. Are you there, Bean?
Indeed, yes, I am. Thank you.
Excellent. Let me get your slides.
Technical glitches. I'm here.
Good man, Bean. Yeah, over to you, Bean.
Thank you very much indeed. You can pop on to the next slide. I just wanted to deliver a few moments on the importance of the connection notification process. Not from a technical perspective. You've heard plenty of that already from Stratwood's presenters, But for future policy perspective, it's really vital that we have important data. So the first couple of slides here I've included because for any installers who are on the call, this has just got the appropriate links to various resources available through the Energy Networks Association. So there's a couple of links to their website, and there is the flowchart process for determining connect and notify or prior consent. Next slide, please, Richard. With a number of manufacturers' representatives on the call, I sort of hesitate to deliver a manufacturer's perspective, but I think that the key here is for manufacturers to ensure that they get as many of their devices as possible onto the database. And I think those that are sitting in on the call have probably got most of their devices, if not all of them, onto the database by now. And there's been some really good development from an early start with that database. We have seen a huge number of devices now included in it. The links are there. I also wanted to touch on the progressive move to three-phase connections being made available in smaller dwellings. Many of you will be aware of Western Power's move towards putting three-phase connections into all new supplies, and also wherever they can when they are unlooping services. So this then raises the question, will manufacturers start to bring in smaller three-phase devices into the UK? And that again will extend requirements to get these machines onto the database. And three-phase has a value for flexibility, which I think we have really got to pursue, and that will include delivery of things like thermal storage. And we're doing some very early work with Ofgem to identify the value of that flexibility in the domestic arena. Clearly, we've got separate issues around flexibility and separate values for flexibility with commercial heat pumps. But in the domestic arena, Ofgem have had a sort of light bulb moment when they realised that actually there is probably significantly more flexibility to be had from domestic heat pumps than from domestic electric vehicles. Next one, please, Richard. So why is connection policy important? So apart from the technical issues, in a digital and connected world, data underpins absolutely everything. And that's government policy, it's Ofgem's analysis, it's the future energy scenarios, FES and DFES. Who wants the data? We're constantly asked by Committee on Climate Change, DNOs, of course, in their network planning, and we've been heavily involved with them through the development of their investment plans for ED2. And that's been really refreshing. I think we've seen some really good levels of understanding and interaction with the DNOs and with the Energy Network Association. Training houses, they need data. Local authorities need data. Manufacturers and distributors need data. They need to be able to plan their inventory. And financiers also need data. And one of the big challenges for our industry is going to be future funding. There's no doubt about that. And so we need to be able to provide as much data as we can to all of these players, because that's what will enable us to drive the item at the top, government policy in favour of heat pump deployment. Next one, please, Richard. So where are the data touch points at the moment? Well, we have MCS, obviously, are collecting some data, but with a restricted mandate at the moment. So currently of limited value. Local authorities, statutory requirement to notify, but this is routinely not complied with. And it's a disjointed data set because there's no real joined up connection between those data sets within authorities. DNOs provide potentially a centralized point for data to be connected through ENA mechanisms or whatever. And they need it for network planning. And there was a piece, probably 3 or 4 years ago now, when Western Power had discovered something like 15,000 unregistered items on their network. That wasn't just heat pumps, of course, it was other devices as well. Clearly manageable in thousands, because the network hadn't fallen over. But we want to get to millions. And at that point, we absolutely need to know what we're doing, where we're going, where these machines are, and where the investment in the networks need to be. So it's vital for network planning. We need to make it easy for installers, and I think there are developments, and I don't know whether Dan might touch on these at some point this morning, developments on trying to make the whole process much easier, the notification process easier for installers. And data will drive everything, including calls from our side for competing technologies to be treated equally. So things like resistive heat products, IR panels, etc. Next one, please. And finally, I just thought it was worth highlighting what the flexibility value is going to be. So this is a snapshot from a report issued by Carbon Trust and Imperial College last year, and they have estimated a value of £16.7 billion per annum on flexibility by 2050. So that's the size of the prize that our industry can aim for. So my plea here is, let's get the connectivity policy correct. Let's make it as easy as we possibly can for installers, and then let's use that data to drive policy that will significantly increase the rate of electrification of heat in the UK. Very much.
Just a quick question, a very quick one there. MCS, what does that mean? What does it stand for?
MCS, sorry, we all assume these acronyms are well understood. Microgeneration Certification Scheme. So it's the industry standard scheme, industry-led, was owned by government, has now been novated into the ownership of a charitable foundation, with the MCS service company operating underneath, and they are cross technology, so it's all low carbon technologies, so PV, solar thermal, biomass, batteries, and they look after and manage a number of standards, installation standards.
Excellent, Bean. Thank you very much. Very good. Bean's around at the Q&A at the end. In the meantime, we're going to go over to Paul.
Yeah, good morning, everyone. How are you? How are we?
Thanks, Paul. You're going to talk about Rio, not the place, the next regulatory price control. You've got some interesting numbers on future projections and what's coming down the pipeline. Can you kick off by talking about that, please?
Yeah, I suppose one of the more interesting ones is the Prime Minister's 10-point plan of 600,000 heat pumps being installed by 2028. This is a 20-fold increase in current levels. BEIS has a medium scenario showing over 1 million heat pumps being sold annually by 2035 in the UK. And this equates to approximately 4,000 heat pumps being commissioned per day.
Sorry, so I guess it's a lot of sort of new devices. Immediately we thinking, how are DNOs going to accommodate all of this, Paul?
Yeah, they need to ensure that suitable networks exist for all heating requirements. This can include, things like new build infrastructure where the network is designed to cater for necessary load, so heat pump demands can be built into the initial designs.
Yeah.
Where there's retrofit installations of heat pumps, the overall demand on the network will increase.
Yeah.
And this could perhaps cause a higher level of demand than the original network design catered for. So yeah, a lot to think about.
Retrofit is I guess the real dilemma, isn't it? I mean, putting in new infrastructure you can account for it, but having to go back and change things. So what do you see as the particular pinch points, I guess, in those sort of legacy networks?
I mean, Assad mentioned this earlier on and was a main part of his talk, and mains and service cables may become constrained and may require uprating as a result of heat pumps. But I know this session is all about heat pumps, but there's other low carbon technologies that are being connected as well. So we need to consider that, which we'll come on to later on. There is also legacy design systems, and one in particular is loop service cables. where these the service cables are shared between two properties. For example, post-war housing, terraced housing, semi-detached housing, you have one service cable going into one house, and then there's a loop into the property next door. These will have to be reconfigured so that the property installing the low carbon technology will have its own service cable, and that's not insignificant. And Dean was mentioning this in our chat earlier on prior to the webinar, but you know, that could be up to somewhere around about £2,000 per new service connection.
And I guess the nuisance or the disturbance to the consumer, digging up drives, whole streets, I guess that's quite a logistical headache to upgrade a whole street, take it off loop services and make it individual.
Yeah, that's a good point. But you know, DNOs, and not just DNOs, but other utility companies are looking at things like trenchless technology, where they don't have to dig up the whole street and they only have to use, excuse me, strategic points for the holes. So things like moling, trenchless technology, that type of thing. DNOs are starting to employ that kind of thing.
Yeah, very good, Paul. So I guess that's one element is the pinch point. So what's Rio ED2 got in store for us in terms of plans?
Well, yeah, the DNOs are looking at a whole range of things to try and improve the process. Being mentioned, the whole connection process for installers. So network companies are looking to improve that with an end-to-end connection process. This includes automated quotation services. So you can just apply, notify, and then the whole process is automated and quick checks are done. And they will say, yes, it's absolutely fine, go ahead. Or no, we need to do some work around about this for the reasons that I've discussed. And I think Dan would like me to reinforce that there is a requirement on the installers and customer to at least notify the DNOs of these installations. Excuse me. DNOs are also producing the equivalent of the National Grid ESO future energy scenarios, and these are showing what the impact of the heat pumps along with the other technologies will be. And they're using these to identify hotspots and future constraints on the network and develop strategic investment options. So where are clusters of these technologies connecting, and how are they affecting the network, and what do we need to do about that? And it should, going back to the Prime Minister's ambitious plan of connecting 3 million heat pumps by 2028, I think it was. The DNOs are predicting somewhere between 2.5 and 3 million heat pumps being connected by the end of Rio ED2. That's during ED2, I should say. Sorry.
Wow, that's a big. That feels like a big number. Apart from sort of refining the connection process and future energy scenarios, what other things are DNOs looking at during the next 5 years?
Well, there's 2 or 3 things that I think are worthy of note. There's monitoring, both on the high voltage and low voltage networks, where the DNOs can gather a lot of information, and monitoring is relatively inexpensive, and they can gather information on all the things that we've been talking about earlier this morning, on harmonics, flicker, load profiles and trends. Again, this will help not just from desktop exercises that I've mentioned, but also it'll provide real-time information on how the networks are performing and if any network constraints are starting to develop. And I'll come on to this in a little bit, but also help support the connection of LCTs and understand what's called flexibility within the network circuit, which isn't just about reinforcing the networks.
Yeah, that comes back to Bean's point about data, building a trend, building knowledge of where the constraints and hotspots are, Paul.
Yeah.
Sorry, go ahead.
No, on you go. Sorry, Richard.
If we think you mentioned there 2.5 to 3 million, was it by 20? Well, during Rito ED2, that's a lot. And I guess if we think about individual homes, how does that impact the profile, the load profile of individual house, Paul?
Yeah, so for the ED, within the DNO's ED2 business plans, they've actually started developing some load profiles for low carbon technologies from a number of different sources, from their own individual innovation projects, from the UK Renewable Heat Premium Payment Database. And the figure here is taken from one of the business plans and shows a typical domestic heat pump for, I think it was 100 heat pumps in ADMD, applying after demand, after diversity maximum demand, using an 8 kilowatt air sourced heat pump. And it shows that the heat pump demand increases by just under, I think it's 1.24, but I've rounded it up to 1.3 kilowatt ADMD to the LV network demand in the early morning when everybody's getting up and making a breakfast and listening to the radio or watching breakfast television. And similarly, in the evening around peak times, it's adding 1.1 kilowatts demand to the network. Yeah, heat pump. Just
to clarify, that is the I guess the average demand if across a large group of consumers. Individually, we're looking, maximum demands is a different consideration, Paul, isn't it? That's where you're actually determining what is the maximum demand if they switch on that heat pump and it's doing maximum output. This is an averaged.
Correct.
Yeah, that's important just to stress that.
If you were to take the maximum demand, I think there would be absolute panic.
Yeah, luckily not everybody showers and does things at the same time. So let's take your values there and ask what does it look like if you put it across these huge numbers that you're predicting? You've extrapolated.
Yeah. So we've got another figure here which shows peak demand tripling with the uptake of both, say, electric vehicles and heat pumps. Now, as I mentioned, if we just take the heat pumps alone, increasing by approximately 1.3 kilowatts, and you take the lower number of the 2.5 million being installed during ED2, that gives an increased demand of approximately 3.25 gigawatts during ED2. Now, just to try and put that into some perspective, that's the equivalent of a new Hinkley Point C that's currently being built and will come on. If we take the PKDMD for combined low carbon technologies, that includes electric vehicles, you're looking at approximately 3 kilowatts at peak demand in the evening. And that's given an increased ADMD of approximately 7.5 gigawatts during ED2. So these are significant numbers.
Yeah. I mean, I've just seen a comment from Bean. It's true about this peak could be moved around a bit with time of use tariffs. These are already establishing for charging of cars.
Yeah.
Moving habits, pushing people's sort of decisions on when they want to turn things on. That could shift things a little bit. Have you seen anything on time of use tariffs, Paul?
Right. Definitely. Time being well done. Thank you. This is my last slide. So big thing that DNOs are looking to move to is the distribution system operator environment, and ENA's Open Networks project is leading on this, not just within the UK, but also globally. And a large part of that is called flexibility services, where the DNOs are looking to manage the networks via flexibility, shifting that peak load, that demand roundabout across the 24-hour period, and not just reinforcing, updating the cables when the limit is reached. There's various elements to this. The DNOs can use aggregated smart meter data, network monitoring, and enhanced analysis that we've talked about to identify where the constraints are. And they're also looking at how loads can be managed to make the greatest use of the existing network capacity, like electric vehicles feeding back into the network at peak demand times. And this will involve steps including incentive mechanisms, possibly time of use tariffs, that kind of thing, to incentivize the customer on how they use heat pumps and electric vehicles and probably disturbing loads.
Yeah. I guess it's a very new concept still, but there's a lot of thoughts and plans have gone into this, and I mean the flexibility market is active, probably more at HV than down to LV, I would say. DNOs go out annually, or is it?
Yeah, Dan might be able to remind me on this, but it's either annually or twice a year. I think they go out round about now, and they also go out round about autumn time.
Yeah.
And currently, I think they're looking. The last figure I saw was just short of 3 gigawatts within the flexibility market.
Yeah.
Across the UK.
Yeah, it's a really interesting, how DNOs are trying to, cater for security of supply using flexibility, but it's a big part of their ED2 plans. Just before we take some questions, I wanted just to flash back. I think Bean did mention this. Sorry, the ENA website, and Assad, you'd mentioned that I flashed over it, but just quickly explain the heat pump database, Assad.
Yeah, so the link is there. So on the database, you'll find the current list of heat pumps that can be, or that are allowed to be connected to ENAs or the network operator's network. But also you'll find is guidance notes. So the guidance notes helps manufacturers, installers to fill out the Excel spreadsheet, which is the submission file that we use and we review. So the link to the database, if you click on that, and you should be able to then access the guidance notes as well, which should help. And obviously, if you have any questions, you can come either directly to myself or Richard.
Yes, thank you, Assad. We're at the point where we can start dealing with some of the queries or questions that have been flagged up. I'm going to just roll back on the chat and try and answer some of these. The first one there is how do you profile inverter driven heat pumps? I'm happy to give a thoughts on that. I guess Chelika was talking about a steady state style heat pump, so a heat pump that starts with a soft starter and it would get up to speed and would run at a fixed speed. So inverter driven heat pumps are variable speed. They're going to just tune their running to the required temperature. So when we're assessing a device like that for flicker, what is really important is the operating cycle of that heat pump. And let's take, for example, a washing machine, which is good to think about. If you're going to assess a washing machine for flicker, you would need to assess it across probably 2 hours, because it's going to run steady, it's going to run down, it's going to run back up. There's lots of switching points for that motor, and like in an inverter driven device, you pick a typical operating cycle. I think 3-3 mentions 2.5 minutes, but it has to be set by the manufacturer, and you have to take a decision on what is a typical operating cycle that's repeatable for that inverter driven heat pump. So it's less easy to do it via desktop calculation, and it's more likely that you would have to use a lab test to determine flicker for an inverter. Next question there was the difference between source impedance and loop impedance. Thanks, Kyle, for that question. That's a tricky little one there, and the terminology is always tricky. We talked about, Assad was talking about the impedance that the motor, the heat pump sees. Quickly, Assad, what a quick explanation of what source impedance and loop impedance would be?
Yeah, so the source impedance is basically your three phase to earth or phase to earth impedance measured at the connection point, whereas your loop impedance, which is generally typically called your earth fault impedance, is at the earth fault loop impedance at the connection point. So that's basically the path the fault current follows when there is a fault on the network.
Yeah, one's important for, I guess, flicker and harmonics. The other's important for protection calculations. Next one is an interesting question there from Guy. Thanks, Guy. That's a good question. So let's say it's a plug and play device. Now, I bought an air conditioner last summer, and it's plug and play. Now, when I bought it, the first thing I would say is rating. And I'll let Dan come in on this as well. P28 is exempt under 1 kilowatt. Chelik and Assad can scream at me if I'm wrong there. So probably the size of the device is exempt from decode. But if it is, sold, CE marking will confirm that it meets the standards. And I remember when I bought that one, I remember looking for a CE mark. So if it's CE marked and it's a plug and play, then it's off you go. Anything you want to say, Dan, on that?
Yeah, I completely agree. The decode states disruptive load, but if you're plugging into a 13 amp socket and you're compliant with the appliance standards, then that's not considered disruptive load, so you can carry on.
Yeah, so hopefully that's clear. We talked about the micro power certification scheme. Some thoughts there on numbers and MCS, the renewable heat incentive, the closure of that. Just quickly on that one, Bean, just give us a quick summary of what was closing and what's now.
So the that number that I just thought was interesting that Paul had highlighted 4,000 units a day. Just under 4,000 domestic heat pumps were certified under MCS during February this year, which is a significant uplift on the same month last year. This reflects the rapid approach now of the end of the domestic renewable heat incentive scheme, which closes to new applicants on 31st at midnight on the 31st of March. So a few days away now. It's being replaced by something rather bizarrely called the boiler upgrade scheme. But anyway, name aside, that's the replacement. Significantly less valuable in total cash terms in most instances, but and particularly for ground source. But it does provide an upfront grant, so it reduces the need for the consumer to have 100% of the capital available at the front end. So it's obviously the closure of the scheme of the RHI is driven significant deployment over the last 6 months. It's coincided sadly with a period of supply constraint. We've got global supply chain issues in all sorts of industries, but I think many manufacturers have found it a bit of a challenge. But we're still managing to deploy record numbers, which is great.
Thank you, Bean. Sorry, you may hear banging in the background. Somebody's banging on my wall. Sorry about that. Loop services, neighbours, disputes about unwillingness to let their drive be digging up if the adjacent wants it upgraded. Paul, any thoughts on that, or anybody else want to come in on that one?
That's a really good question. I don't know if anybody from a DNO who's involved in this type of thing is, but I suppose this comes down to discussions with both between the neighbours, with the DNO and DNO way leaves, you know, but I would suggest that it's probably within the customer's benefit to have their own service cable. So I haven't actually heard of any disputes between about neighbours, you know, not wanting their own service cable. But I suppose that would be for the DNOs to resolve.
I can imagine a nice mosaic hallway in a period property being smashed up.
The one thing I would say is that whatever the property, you know, the DNO is will endeavour to reinstate, you know, the property to at the very minimum what it was previously, and that would be negotiated via the way leaves department and also the people carrying out the work.
I agree with that. And it's one of the issues with networks is there's such variability out there, you know, with houses, with geography, with distance to substations. You know, it's very difficult to create a one-size-fits-all policy. So it would have to be tackled on a sort of case-by-case basis, taking those idiosyncrasies into account. So yeah, I fully agree, Paul.
Yeah.
Thanks, Paul and Dan. I'm just going to run through a few more here. Monitoring, what monitoring do DNOs currently have? And I would say it's over the years been quite minimal on LV. It's been a passive network, so you know things like MDI, and this is maximum demand indicators where they're just read on site. But I do think DNOs that over the last couple of years have been putting on some more remote control switching, some more monitoring of transformer voltage levels. Some are going for tap changers on distribution transformers. But as I say, I don't think it's been a great deal on LV. Any thoughts from anybody else?
Yeah, what I would say, Richard, is that this space within the innovation area moving into ED2 is certainly ramping up. Things like fuses, takeoff chambers or at the transformer, fuses are now being incorporated with LV monitoring, and this can monitor load and the harmonics and flicker that we've actually. So this is at the start of the low voltage feeder. An example of this that is just starting to come onto the market and be tested is Kelvitech's Presense LV monitoring, and that's as a result of some of the innovation projects that have been being carried out within the DNOs.
Yeah.
So it's certainly an area that is ramping up, and I would expect to see this be huge over the coming years.
And there's also a lot of innovation projects looking at modelling the LV network and trying to take what limited data there is from physical monitors and model the rest of the network. And it's as Beam was saying, it's another really important way in which more data can support networks to provide a more efficient and flexible service. So notification of heat pumps being on a network will just all feed into that model and make it as efficient and valuable as possible. So really, really important question and really important points that Paul made there as well.
Thanks, guys, again. Housing estates in the winter having to be re-energized after a period of disconnection. If they've all got heat pumps, this is a real headache, this one, I think, for DNOs in the future. I think the reality is there's very little experience yet of it. There's probably two ways into this one, and the first one is network segregation, and I think that's about LV mains and breaking it into sections and DNOs re-energizing in sections to control that inrush to avoid tripping fuses back at the substation. The second way is controlling at the point of supply the consumers, you know, which ones you're going to switch on. That probably requires a lot more sophisticated equipment. I think at this point DNOs probably favor controlling their network, taking the network into their, you know, that's their That's their sort of gift to sort of control how they're going to re-energize networks, and that's probably where we'll see things go. But I think there's limited experience still on this.
Yeah, there is an example from the ChargePoint, electric vehicle ChargePoint smart meter consultation that BEIS are recently running, where they're looking to include a randomized delay function for all smart meters. And that would allow there to be a period where the charging of the vehicle doesn't start all at exactly the same time. So it's not an instant point of charge, and there's each charge point has a slight randomized delay function over, I think it's 10 minutes, with the ability for that to be extended to 30 minutes. And that will just give networks a little bit of a chance to revamp the whole network before everybody starts charging their vehicle. There isn't the same stipulation at the moment for heat pumps, but as been pointed out in the chat, that's something that's being looked at, and what the options might be for heat pumps as well.
Oh, excellent. That's a good insight. Thanks, Dan.
I think, Richard, that also a couple of the DNOs are also looking at this. Again, a couple of innovation projects, possibly over the next few months, to have a look at the cold load pickup and how they can manage that. And it's not just, as Dan has mentioned, electric vehicles, but it's also heat pumps and other technologies that are coming on as well, how they can manage that.
Mindful that we're over the hour, I'm gonna move on. I'm gonna plow on till 5 past. If people want to hang around, please do. We're gonna try and see how far we get till 5 past, and then we'll do a hard stop and break for a cup of tea. Heat pump database, Assad, and there's a question there about that. Sounds like where early heat pumps were added, they were complying with G5, G54, G55. Is that relevant to the heat pump database?
Not really. I mean, G54 and G55, I think the limits are still the same. I think there's a bit more information on stage 2C connections, which are heat pumps that are not compliant with the 3.2 and 3.12 standards, so 61,000 series standards. I think that's where G5 sort of comes into play. But the heat pumps on the database currently at the minute are all heat pumps that have been assessed according to 3.2, 3.11, 3.12. Obviously, any heat pumps that do not comply with that, that's then with the DNO to do a further detailed assessment on, which they then use G55 to do that.
Yeah, I don't think there's been any significant changes. There hasn't been any in the 61,000 series, so everything stands okay on the database. Manufacturers comply with is it connect and it's guarantee. Question here about the Emc Directive. If you comply with it through the product standards, is it connect and notify? I'll quickly answer this. Assad can jump in. Number 1 is the current rating. If you're above 32 amps, it's not. You've got to apply to connect. And the second point is there could be a minimum impedance which has been stipulated during those EMC tests, so which would make it apply to connect. So it's not a given. If you comply with the standards, the product standards, could be a condition in there. All your data is 0. Mandated randomized start, power up, good. We may all end up cooking with electricity rather than gas. That's true. So managing black starts will be important. Yeah, showers, cookers, heaters. Guys, we've got to the end of our time. I think I said go to 5 past. I'm going to call it to a close there. Thank you to Bean. Thank you to Dan for your time supporting this webinar. I hope everybody found it helpful, useful. Maybe it posed more questions that maybe could be addressed in the future. We will send this recording out, and our details are on the end of the slides. If you want to contact us or get in touch with Bean or Dan, we can put you in touch with them. But for now, have a good day, have a nice weekend, and check back with the ENA's website. There's a Smarter Network portal as well, and see you all in the next one.
Thanks, everyone. Goodbye.
See ya.
Bye.